Okay, good. So just to see a few people who were not here before, so let me just to remind you where we are. This is a problem studying. So there's a large cloud of dust. I want to know what happened in the future using classical and where is needed quantum physics, okay? This is modeling. It's not a mathematical physical model. It's a patchwork of understanding what happened when it's in the various stories. And I am separating the dissipative part of the story from the non-dissipative part of the story, like we do in a bounce. And this first lecture, I've done the non-dissipative part of the story, and in this lecture, I'm bringing in the dissipative part of the story, which is correct, of course, and quite heavily what happens before. And I've said that the star itself, it's easy to have a very good educated guess of what happened, and this is the bounce of the star through a minimum size, which is not Planckian. It's Planck density. It's not Planckian radius, it's Planck density. Outside, we have a great guess of the metric for a number of reasons, a large number of converging, beautifully converging reasons, which is this metric here. Okay? This is a metric we have been working with. The maximal extension is that, but I said it's not reliable here for various regions, so there's something wrong here. So this part here is not reliable, which suggests that we may actually can identify this part here of Sky plus with the continuation of this part here, Sky plus, and we can actually do the geometry of constructing a space-time which has a property which is described by that metric all around a region we have cut away and of which I haven't told you much at the beginning. And this is beautiful properties, this metric here. This is not a solution of Einstein equations, of course, because there is some h-bar correction here, so to linear in h-bar, actually. But this horizon here and this horizon here are far away from the quantum region, okay? And which means that remarkably, this is a solution which, if you forget the quantum region, which is sort of this one, it's Schwarzschild continuing in a black hole in the past and a white hole in the future. Trapped surface in the past, trapped surface in the future. This seems impossible if you think of Birkhoff theorem, but it is possible because Birkhoff theorem is local, it's not global. So that's not a subset of Kruskal, but is a space which is locally isomorphic to Kruskal. And you can close it inside with that metric that I gave you, which is this little correction h-bar. And we do it, you get this extra constant, which I gave you the geometry of the extra constant, which has to do with how long is the process outside. And I told you inside the process of the order of m in natural units, outside it's undeterminate by that metric. It's depending how you glue, you can glue it longer and closer. So that's the, these are the actual metric. The constant comes from this integration of that integral there. And I said that the remaining region, the B region, is naturally described is easily described in this formalism that Francesca Ronguan described in great details, because it's a transition between the initial state and the final state, where you compute probability amplitudes for going from here to there. So you sort of use quantum mechanics by saying, well, this is where I can disregard quantum mechanics, so I can treat classically, and then the quantum mechanics think I see it as a probability jump, right? When you do standard quantum mechanics, say my quantum mechanics phenomenon is here, I measure something, and then a probability distribution will happen there. It's like I'm measuring there. From the moment in which you have the coherence or whatever, that's where you use probabilities, and that's how you use quantum mechanics always or mostly in physics. Concretely, you can do the calculation So using the technology that Christine and Francesca and Hongwan described by a triangulation here, a triangulation there, and a triangulation inside, and you're computing this probability amplitude in a truncation. So you only look at large degrees of freedom. So you're ignoring the high frequency modes, just looking at the high one, and you do this this computation. This computation is far from obvious, and the three or four papers that study this calculation is pretty heavy, and I'm struggling to find a short version of the calculation, but I think the key should be extracted in some simple way. But the general result, one general key result that one can derive is that the amplitude for such transition depends on the parameters of the mass, this extra constant that says how time it takes. But what comes out pretty easily is that it's the amplitude is proportional to this factor here. The mass appears there. Okay. Now, two considerations. Look where h bar is here. H bar here is e to the minus 1 over h bar. So it's non-analytic in h bar. It's a typical non-perturbative effect, like tunneling. So if you do an expansion in h bar, you don't get it. Okay? It's very important. While inside, the other corrections I've studied in the C region and the A region, these are all first order in h bar. There's a different phenomena, profoundly different phenomena. One is a little quantum correction, which has a big effect globally. This is a tunneling. What happened near the horizon is a tunneling. Okay? So it's nothing you can get analytically in h bar. These are the typical formulas when you do in elementary quantum mechanics, right? You have a potential barrier, you have a wave packet, you have classically, I think, bounces back because the energy is less than the height of the packet, but you have a probability of tunneling. You compute the probability of tunneling. There are 2 or 3 ways of doing these calculations. Yesterday with John Engel, we were saying it's always strange you do these calculations, no clean connection to measurement theory. But you do this calculation, and you get probabilities of jumping the other side of doing something non-classical, and it's non-analytic in h bar, right? The T and R coefficients have that dependence on h bar. There's a recent paper with Hal and Pietro Donà and Francesca in which we study tunneling, quantum tunneling of geometries from one geometry to another geometry, which cannot happen classically in three-dimensional theory where everything is simple, you can compute everything. And we show that also you get something like that. That's another way of viewing it. Another way of viewing it is that the amplitudes, remember, we expect the amplitude to be proportional to the Regge action. You will have lectures on the Regge action. The Regge action is a sum of area, surface, spin, as you have seen, times angles. But when there is no Lorentzian geometry that allows you to this transition, this angle come out imaginary. Again, this is standard tunneling. So you get an extra I here. So you get minus no I, and here the areas. So once again, e to the minus the areas, which is that formula here. It's m squared. Area is the radius is the mass. And h bar, of course, goes down dimensional. All right, so this is to give you a sense of where we are. Now, if I stop here, it's pretty disappointing because, all right, so a big black hole basically has a probability of going down, which is e to the minus is mass over the Planck mass square. Oh shit, this is, not even many times the Hubble time. It's many times the Hubble time for any macroscopic thing. So that seemed to be totally irrelevant for physics, but there's a dissipative effect. So now second hours, oops, time flies. Let's look at the dissipative effect. And picture is going to change. So first of all, as I said, the obvious dissipative effect is the Hawking radiation. The Hawking radiation is a quintessential dissipative effect, right? It's irreversible. One way to think of the Hawking radiation is that you have the energy concentrated in the form of mass, and then it becomes radiation all over the sky. So it's profoundly dissipative. If you time reverse it, you have all this thermal radiation that concentrate and give rise to stars. So it's a quintessential dissipative things. And as I said, because of back reaction, the radius of the horizon, now we're talking about a dynamical horizon, apparent horizon, trapping horizon, not an event horizon, right? We don't know what's happened there. It goes down, which means that outside the horizon, the curvature becomes r squared. When because of the back reaction, the radius becomes Planckian, the curvature becomes Planckian, and therefore you're in a quantum gravity region there. So how long does it take? Well, this is standard Hawking theory. One way of viewing this is the following. The radiation, the Hawking radiation is thermal with a wavelength. I don't know which one I want to go on. You can go this way. Seen from a distance, the Hawking radiation has a wavelength which is given by the only parameter around is the mass of the black hole, which is radiating, right? And it's, as Hawking has shown, is thermal, so you have a Planck spectrum which has a maximum at that wavelength, the corresponding frequency, which is one of the wavelength. So so this is the energy. So kT is E because it's thermal. So what you get from here directly is that the temperature is proportional to the inverse of the mass. And then you model this as a surface of radius m square, which is the horizon at that temperature, and just standard thermodynamics tell you that emitted power, which is also the change of the mass in time, is proportional to the area times the inverse, the fourth power of the temperature, which you get 1 over m squared. You integrate this equation, and you find that the change of the mass and the time is that t goes to m cubed, which means that the time it gets to get to zero, to Planckian, to get to the quantum region, is of order the original. I put a 0 because it's the original mass to the third power. So what we expect is that this sphere, it's collapsing, and from the outside, after a time m cube, we are in the domain of which I was describing where the transition can happen. And let me just make a parenthesis. This is a picture that is very common in discussing what happened in black hole radiation. This picture, namely the idea that the mass here goes to 0, then there's nothing left, and so we're back in Minkowski. There is no theory that predicts this to happen here. So this is a picture, in fact, it's Hawking, the first one who drew this picture in a paper where he said very, very clearly, of course, this is not reliable because we don't know what's happened here. Okay? What happened here is exactly what I've been discussing at the end of the previous lecture, what might happen there. Before going ahead, maybe it's a good moment to get a geometrical picture of what is going on. Take a constant Cauchy surface, a time-like surface in the classical region, crossing the horizon at some point. And look at the geometry of this part here. And the geometry of this part here, if you write it in if you choose a foliation appropriately, and I'll say in a moment what is appropriate foliation, it's easy to write down and it's easy to see what's going on. The geometry, if this is the horizon here, the geometry of the surface is like a longer tube where the falling star, the star that collapses, is down here. And as you go to higher and higher, if you follow the foliation, what happens is that this becomes longer and longer and it shrinks. So it becomes like that. And of course, if you follow classical GR, it gets to a point. And if you do the metric that I described, it gets to a minimum size and then bounces back. Okay? It's important because there is a common intuition which is wrong, which is the idea that the singularity is here. Singularity is not there. The singularity is everywhere in the future. Singularity is it's like that. It's like that. So the singularity is not in a where. It's in a when. It's like if you enter in a room, look for the singularity, you don't find it. Everything is squashing around you. Okay? It's some time that happens. So that's when the interior transition can happen. And what is important is that the volume of this region, how do you compute the volume? This is depending on the choice of the foliation. But there's a preferred definition of the volume, which is once you fix an area, when you fix a surface here, you can define the volume inside as the surface that has the maximum volume. This is what you do in Minkowski, right? In Minkowski, if you have a two-dimensional sphere, two-sphere, the volume inside is the maximum volume because if you move it up and down in time, the volume becomes smaller, of course. If you go to a light cone, it becomes 0. So the volume inside a sphere in Minkowski can be defined by resorting to linearity, or it can be defined as the maximum, the surface that maximizes the volume. And that definition extends to an arbitrary Lorentz space-time. And with that definition, you can define a preferred foliation. For every point on the horizon, you have a preferred surface inside. This was defined in my paper with Marius. And you compute the volume, and the volume increases as you go on. So the black hole becomes bigger and bigger and bigger as you go ahead, even if the back reaction shrinks the apparent horizon outside. So that's important because when you go to the towards singularity, it's not that the inside is becoming smaller, it's becoming bigger. The full space inside, that's going to play a role in a moment. Okay, so in an actual space-time, we start with a mass m0. There's Hawking radiation. We're deep into dissipation effects, deep in irreversibility. This becomes smaller and smaller and smaller. Okay, now we can apply what I said in the previous lecture. After the mass has become small. And now the exponential depressor e to the minus m squared over h bar is not suppressing the transition. So you expect the transition to happen with some probability. And one way of thinking of this is that you break your time in your classical time in steps in an arbitrary number of one smaller step. But each time you have a probability of jumping or probability of remaining what you are. So at every moment you can have a probability of not jumping or jumping. But as you don't jump, the back reaction is shrinking the mass, so the probability of jumping goes higher and higher and higher and higher, and you expect this to integrate to 1, so you actually jump at the end. Okay? And you are from this surface, which has one sort of extrinsic curvature, to the other surface, which has the opposite extrinsic curvature. So there's a jump in which the extrinsic curvature of the lowest changes to the extrinsic curvature opposite sign, which if you think is exactly what happened in tunneling, right? In tunneling, you have one tunneling of a potential barrier. You have one probability of changing the direction of momentum, one probability of preserving it. And you can reduce the entire calculation in a two-dimensional Hilbert space, fixed energy, k this way, very, very small dimensional Hilbert space, do a calculation there. So I hope this is what should be done here. Reduce the entire calculation in a two-dimensional Hilbert space, okay? The initial surface to have a certain intrinsic geometry, a certain extrinsic geometry, and the jumping surface, the same intrinsic geometry and the same extrinsic geometry with the other sign. All right, so in terms of the internal geometry, this is what happened, right? So you get to a maximum volume, finite, a maximum size of this, finite, determined here by the density of the star being Planckian, here by the curvature being Planckian, and here is a non-analytic part of the transition, non-analytic in H bar part, in which you have to resort to other ways, like this calculation of transition amplitude. What about, let's suppose that this is what happened. What about the energy? Because, let's go back. The mass of this has gone down to a mass close to the Planck mass. So this horizon here has an horizon which is close to the Planck mass. It's small. It's very small. Okay? There's no residual. The energy has gone out here. So there's no residual energy here, whatever energy means here. If you start from a macroscopic black hole, you don't expect a macroscopic black hole, white hole to come out. So what happened to the energy? Well, the Hawking radiation we don't have exact calculations of the energy flux, the energy and energy flux of the Hawking calculation, but we have a lot of approximate calculation, for instance, two-dimensional calculations, which are supposed to mimic what happened in 4 dimensions. And what is really convincing is that there's an energy flux going out, of course, that's easy, but there's a negative energy flux going in. So the Hawking radiation includes, in 2 dimensions it can be computed on the horizon explicitly, the flux of the energy on the horizon. So you have a negative energy going in, and of course the star itself has a lot of energy, and the two are going to meet somewhere. So the negative energies of the Hawking radiation and the positive energy of the star, whatever happens, necessarily annihilate one another. So the star that comes out, remember, the star is bouncing, come out, but what comes out is a much, much smaller energy than what goes in, necessarily, because inside is all the energy of the... So if you think at negative energy going up in terms of conservation of energy, it's like energy going back in time, right? That's just a way of thinking. So the path of the energy is go in with this star, comes out with a negative energy Hawking radiation, and going to the there. So it ends up on, it's all NS or Sky plus in the form of Bondi energy here. So you expand Bondi energy, so radiation energy here. So the energy that was originally in the star, it's sort of dissipated all over in Bondi energy here, but not entirely, because there is a small white hole still remaining, about which we're going to talk. I'm going to talk in a moment. But what about information? Careful, energy is not the same thing as information. There is this story about the so-called black hole information paradox, which claims that there's a problem with information inside. Energy is not necessarily connected to information. Information means if we know the state at on some previous Cauchy surfaces, does it determine uniquely the state on some later one, and vice versa, okay? Of course, careful. If I'm computing transition amplitude, I'm projecting on something, I'm losing information, okay? That's not what I'm talking about. But if all the Hawking radiation coming out is correlated with the Hawking radiation coming in, where does the information about this quanta come in? And if the state here is thermal, is not pure, that's perfectly possible because it's purified by the entanglement with what comes out, with what is in. Can the information be trapped here? And can it stay inside and come out from the white hole, even if the energy goes out before? And the answer is yes, of course, because there is no reason that I understand for which small energy should mean small information. In standard quantum field theory, that's certainly not the case, because take QED, to have a lot of information, you need a lot of quanta. There's a lot of photons. So we want to send a complicated message. You can have a lot of photons with, they have two polarization. You have 0, 1, 0, 1. You can put all the information you want. Now, can you have a lot of photons with little energy? Yes, of course, because E is h nu. So if you have amount of energy, you can divide, if you have a fixed amount E of energy, you can divide by n, many photons, n as large as you want. You get energy per photon very small, but that's not a problem. A photon can have arbitrary low energy, provided the nu is small or lambda is very long. So you need a lot of space and a lot of time. But we have a lot of space. It's all this space inside. But we also need a lot of time. Yes? We don't have a lot of time. But
so maybe it's a naive question. So are there precise calculations about that? Because like some people use, for example, techniques from quantum scrambling to kind of estimate how you can recover the information that goes into a black hole. Mostly, I think, in this holographic scenario.
I'm going to that. So
okay.
That's what I'm going to talk about the next 10 minutes. So then come back to the question if I don't answer it now. So I also need a lot of time for the information to come out of the white hole, okay? If conservation of energy tells me that all the information needed to purify the Hawking radiation that arrived here must come out there. So I can do some back-of-the-envelope calculations of what would it require. And what it would require is that if I have some radiation that comes out here, it has to have small energy because I only have a Planck amount of energy, a small macroscopically, still a lot in terms of particle physics. Sort of a lot of particles, which therefore each have low energy, therefore each has low frequency, so each needs a lot of time because most because the period is long. So you can do a little calculation. I'm not going to detail here. You can model the emitted radiation here. It's only emitted radially, so you can model it with just a one-dimensional gas of null particles. And impose that there is a certain amount of entropy of the order of what you need to purify the Hawking radiation, which is roughly that. You have the available energy, which is just a Planck energy, 1 in unit times. And then standard formulas of thermodynamics of one-dimensional gas connect entropy and energy to the temperature and the length on which this is fixed. So you can compute the length and you get m to the 4 because there's m coming here. So that means that you need the energy at least to be on a radial m to the 4, which means that you need a time in which you have to fill it, which means that the lifetime of the white hole should be at least m to the 4th, where m0 is the original mass, to get conservation of entropy, okay? So by conservation of information, one would expect the lifetime, so the lifetime of the black hole, you expect by Hawking theory to be m cube. The lifetime of the small things, which comes after, you expect it to be m to the 4th. So this is a story. The star collapses. And you have a state, which I want to call it a black hole state, which has a horizon of the order m0, the initial size of the horizon, and an interior in which there is a sort of the one corresponding to a black hole created with this horizon. But as Hawking radiation decreases the horizon, you still have a black hole, but you have the interior, which is much smaller than a black hole just created with that smaller horizon. So you get something with a small throat and a big volume. Then you have this tunneling, And what you get is a white hole with a small throat and a big inside. And then you have a long time to bring the small throat, to bring in all the volume inside, have all the radiation coming out before you get to the end. And this is necessarily long for the reason I said. From the perspective of quantum field theory, this process here, which is very long, if you think about it in terms of quantum field theory, first order perturbation theory, you can, which means that the amplitude of this is very small. That's what this a long time means. If you describe this process here, which is one vertex, you have this, I call it remnant, this small Planck-sized white hole. I'll say in a moment how to think about it a little better, which has to go, to first order, the only possibility is jump into a large number of photons, and this has a small probability, which, by the way, explain why you cannot do the reverse, because you cannot at CERN take a huge number of photons, a huge amount of information, and concentrate it just by thermodynamics. But statistically, this is improbable. Now, why this has to be only one vertex? That's the key. Why can't this be a sequence of jumps? Because if it was a sequence of jumps, the energy after one jump should be something intermediate between the Planck energy of the remnant and the zero. So the area of the intermediate state should be less than a Planck area and more than zero. But we have an area gap. So the area gap is what is forbidding any transition. Once the horizon goes to Planckian, the last step from Planckian to nothing has to be just one jump in perturbation theory. So the vertex can only be that. You cannot realize this in perturbation theory as many, many jumps because the intermediate states are not there in loop quantum gravity. So this is a genuine loop quantum gravity result that the area gap gives a gap between this this remnant, which has a Planck area and a lot of quantum numbers inside. That's the point. But all these quantum numbers inside cannot radiate out because they cannot take energy out, right? Because they can also take the energy all together. If you think in quantum gravity, if you think classically, you can think that this is exponentially decay. But quantum mechanics is very clear what's going on. It's the area gap that stabilized that. And let me jump to this first, then I come back to this. I'll say in a moment, I'll come back to that white holes are classically unstable. And if I have time, explain exactly why, and I give you the intuition of why white hole is stable. So a white hole has a probability of being unstable, and they are unstable toward becoming black holes. I'll show you in a moment. So there's a probability for a white hole to become a black hole at every time step. But I just gave you, that was the first lecture, a probability for a black hole to become a white hole. So let's describe this in quantum mechanics, standard things you do in a mechanics. Remember the ammonia molecule. You have just describe this as a two-state system. Your probability going one way, probability going the other way. What happens? Well, what happens is that the system emits all the energy it can and stabilizes in a linear combination of the two, right? You have an Hamiltonian which gives the energy of one, the energy of the other, the probability of one jump, probability of the other. You diagonalize this and you find the lowest energy state, which is a combination of the two. So what you expect here now is not really a white hole. It's a white hole stabilized by quantum mechanics, which you can model as a linear combination of white holes and black hole. Okay? That's what you expect. That's a remnant, which has a low probability, but non-zero, to explode in many, many particles, very low energy particles with all the information needed, and the low probability corresponds to long time, at least m-fourths. Now, before doing the stability story, let me, because it's more important, talk about the information paradox, which is the question you were asking. Now, the information paradox is the idea by Page that the information should come out before the end of the evaporation, in fact, much before the end of the evaporation, because if the number of states inside the black hole is bound by the area, is exponent of the area divided by 4, then there are not enough states inside for purifying the Hawking radiation. So therefore, information should come out before, which is not what I'm telling you. I'm telling you information come out after. So why am I disregarding this argument by Page? The argument by Page is very convincing, because if you think of fireplace, that's exactly what Page had in mind. A fireplace burns, emits thermal radiation, then it cools down, it goes to cold. When it's cold, there's only one state. So there's no way the radiation emitted could be correlated with something in the fireplace because it is just in one state. So all the radiation altogether should have zero entropy, is in a pure state. So if you look at all the radiation, so the late quanta are correlated to the early quanta. So a lot of people have in mind that the same should happen with a black hole. But the black hole is not like a fireplace because inside there's this big volume which all the information can stay out. So why all these people think that the black hole is a small number of states? Because everybody takes seriously this relation that the von Neumann entropy of the correlation of something outside and something inside of system must be less than the thermodynamical entropy, because the thermodynamical entropy just counts the number of degrees of freedom of a system, of the dimension of the Hilbert space of a system, and therefore you cannot have more state than those. But that's not true in general. It's only true if the system is ergodic. So let me give you an example, a very simple example, where you have a system, this system here, which has a thermodynamical entropy which is less than the maximum von Neumann entropy describes the entanglement of this with something else. So take this system, entangle it with something outside, okay, and then break the system in two parts, and you send one very far away and one there. And now let this observer interact with this. And of course, the thermodynamical entropy that the observer sees, he cannot interact with that because it's far away. So the thermodynamical entropy is only determined with the number of states of B, 1. But the entanglement entropy between A and everything, A can be entangled with this, but also with that. So the von Neumann entropy can be much higher than the thermodynamical entropy. So that relation, this relation here, which is what everybody doing Page curve assume as obviously true, is just false, trivially, when there is a part of the system that is not thermodynamically interacting with you anymore, and this is obviously exactly what happened in a black hole, right? As long as you're here, you're outside. So before you pass this, the transition, as long as you're here on this part of sky plus, you're interacting with the degrees of freedom which are here, and the thermodynamical entropy goes down with the area if the area goes down. So the area goes down, the Beck-Stein entropy goes down, the thermodynamic entropy goes down, but you can be entangled with degrees of freedom inside. Now this cannot happen if you, by fiat, take what Maldacena calls the dogma of the black hole dogma, which is the number of states inside a black hole is bounded by the area. So it's a strong version of holography, but that's a dogma that you bring in if you believe in certain approaches to quantum gravity. So it's strongly dependent in believing into certain approaches to quantum gravity. That's dogma, as far as I understand, maybe I'm missing something, but as far as me and my friends understand, is not realized in loop quantum gravity. So you can be entangled, the Hawking radiation come out, can be entangled which was inside, even if the thermodynamic entropy describe the interaction here, it's bounded by the area is going down with time. Of course, if you wait after the transition, then you can recover all the information inside. So the overall entropy of everything emitted is zero, of course. So, but what it means is that the Hawking quanta are going to be correlated with later radiation that come out from the white hole, not with themselves. So you don't need all the funny things that people are doing trying to justify the page curve. I promised you a explanation of why white holes are unstable. That took me forever and all sorts of discussions for understanding it. So let me show you why white holes are unstable and why, therefore, the white hole, we don't expect macroscopic white hole in the sky for thermodynamic reason, not for mechanical reason. White hole is a perfect solution for Einstein equations, right? By themselves are okay. It's thermodynamically very stable. But why we expect small black holes, small white holes, remnants, which are stabilized by quantum gravity. So to understand why white holes are unstable, the best is to think about black holes. So imagine you have a star and a black hole, and imagine there's no incoming radiation. But let me add something. Let me imagine that here there is actually some radiation arriving at some time, a photon, which has been emitted by somebody sitting on the star at some time. And fix the energy here, dn, delta n, of this photon emitted. So here is Schwarzschild, n plus delta m, and here after the photon is Schwarzschild m, and then the radius is r equal to m. And at some point, this guy emits the radiation and goes out. Now, question. Can this point be everywhere and arbitrarily close to 2m? The answer is no, because obviously the energy here is m plus delta n. So it should be at a radius, it cannot be at a radius that is less than the radius r of 2m plus delta m, otherwise it would be inside the horizon. Okay? So there is, given delta m, there is a limit of how late this can be emitted, which means that given delta m, there is a limit of how a radiation can get to Scri plus late in time. And remember, this is infinite. So for every amount of radiation, it cannot get to your distant observer at an arbitrary point in time. There's a bound. So the data here are not free. Okay? If there's a black hole, it's dark there after a while. You cannot get extra light. Forget the Hawking radiation. So the data here are not compatible with the rest of the story unless there is some low reception of energy there. Now let's time reverse it. It means that in order to have, this is a white hole, an eternal white hole, you cannot input energy here, fix an amount of energy delta m, you cannot send an energy delta m here arbitrarily early in time. So for every amount of energy delta m, you can go sufficiently early in time, and this doesn't work. That's quintessential instability. That's what instability is around. You have a solution, you have nothing close to it. Now, what happens if you do? Okay, suppose you do, I mean, you can. Okay, suppose there's a white hole, you do send some energy. Well, the energy comes in. At some point, it is in a radius smaller than 2m plus the energy, so it's inside a black hole. So if you do send some energy here, the energy comes in, but you just create a black hole. So a white hole, namely a an anti-trapping horizon from which matter comes out and then there is no horizon, is unstable toward becoming a black hole, a white hole that becomes a black hole. In other words, if you have a macroscopic black hole here, forever it's unstable because it can jump into a white hole. But this, it's corrected in this space-time I'm describing because the transition white to black, the instability is counterbalanced by the black to white quantum transition. And so what we expect is quantum mechanically the system to sit on a okay, how much time do I have? 10 minutes? Oh, fantastic. So I'm trying to leave as much time as I can for questions. Now, one thing we have done, I just want to mention this, is to think that we have a lot, well, I think I better go down to this first, because that's somehow I want to end up as physical as possible. Now, why this is interesting? I think for one key reason, which I found is the most interesting of all this story. So imagine this story is right. So then black holes, any cloud of matter collapse, a black hole, it's a white hole, it's stabilized, the remnant, and stays there. Okay? Now imagine in a previous pre-bouncing universe or in some early universe, both black hole formed and they become remnants. Remember, M4 is the lower bound of the life of the remnant. Could be, as far as we know, could live more. I don't know how to put an upper bound. Imagine you had a lot of these things. So these are what? These are stable or semi-stable particles, because they live very long, of a mass that we know. It's Planck mass, because there's area gap. The area gap determines the mass of these things. Okay? So it's 20 microgram. It's a small fraction of a milligram. It's a weight of one of your hair, or a little piece of your hair. So it's very small astrophysically, but huge in terms of particle physics. This is the intermediate scale. Okay? And the theory is sort of predicting that there could be all sorts of stuff this around. Imagine there are many. And how do they interact? Well, this is a very teeny radiation that they emit because they are going to die and nothing is eternal. So they're going to emit in this with a small probability. But mostly they're stable. And they all interact gravitationally. So imagine there would be in the universe teeny particles which only interact gravitationally, nothing else, semi-stable, and are there. Okay? They would not be seen, so be dark, and they would matter, and they would fill the universe. So there would be dark matter in the universe. So there is something very tempting here to consider these possible candidates for dark matter. Dark matter is, as you all know, it's a mystery. The most likely, the favorite candidate for dark matter, which was the WIMPs, the supersymmetric WIMPs, is just out. Not out. It's was not found by all the searches, and was predicted by minimal supersymmetric model, which is sort of almost killed by CERN data. So WIMPs are not very credible anymore. So there are other candidates for dark matter, right? Axions, modification of gravity, nothing works very well. So here is a candidate of dark matter. So if in a previous phase of the universe there was, or in the early universe, there was enough black hole formed that had time to become white holes, dark matter could be this Planck thing going around. And I find it very tempting because, look, quantum gravity is a theory with a scale, Planck scale. So it would be strange if in the spectrum of the theory there wouldn't be a particle or a quasi-particle stable at that scale. 5 minutes, thank you. So we want phenomenology of quantum gravity. we have all the early cosmology, but hasn't get to the point in which it's strong and convincing. But there's a hint here that quantum gravity should tell us that there is a semi-stable particle at the Planck scale. And in fact, if there was there, it would be a fantastic explanation of this thing we don't understand, which is dark matter. So do we have a chance to, in a sense, only only gravitational interacting particle, in a sense, is the best candidate for dark matter, because that's the phenomenology we have. It's a thing that interacts only gravitationally. Do we have a chance to see it, to confirm it? I'm going to give you two hints, and this is all open to young people coming in and solving problems. The first is that these are going to emit radiation. Each one of these is going to emit radiation. Of course, very low energy, extremely long frequency, but we can model this radiation if we imagine that dark matter is composed by these things here. So if dark matter is composed by these things here, then we know how much energy is there. We can take as a parameter the unknown lifetime, or we can fix tentative lifetime to be m to the fourth, and compute the amount of radiation that we expect in the sky, given that dark matter, we know how much density of dark matter there is, would be originated by that. And this is a paper by these people here, where there's a little model of this emission of radiation, and the model depends on a single parameter, x, which is the mass of the original black hole in Planck unit in the logarithm of 10. And if you have that, you can compute the frequency and the density of this radiation explicitly. It's a little exercise to do that. So yes, so this is one possible hint, but this is very low energy, this is low density. Can we do better? I think we can, and I just got 2 days ago the positive review report of a paper about direct detection of this dark matter. So imagine you have these little things which have a Planck mass, which constitute dark matter. We know how many they are, because we know the density of dark matter, we know the mass of this, and we know how many they are. And we can estimate how they're moving with respect to us, because dark matter is expected to be essentially cold, it's cold dark matter, and not rotating around the galaxy, but we're rotating around the galaxy. So we're moving in a cloud of these things at the speed that we know. So we know roughly how many of these things fly here at which speed, a few hundred kilometers per second. If you do the calculation, roughly in this room, there's several every year that fly through. There may be one here, one of these Planckians things flying by. Now, of course, they interact only gravitationally. Can we detect them? The answer is possibly yes. And we have this paper where we make a little model by using quantum interference technique. And this was inspired by the experiments, the tabletop experiments of quantum gravity that raised a lot of interest in the last years. So the theoretical idea is the following. Take a quantum particle and split in two components. Take a particle, say a particle with spin, split it with Gerlach in two components. If you're flying by a particle, there is a gravitational interaction with this, which is a little bit different because this is closer, this is far away. So if this flies, if this is very small, I sort of affect this, but not this one. And so there's a little change in the phase of this branch and this branch. So if you say start with a spin-up particle and you split with Stern-Gerlach, spin right, spin left, when you bring it back together, it's not spin up anymore. You have a probability of going spin down, okay? Now, this is a theoretical idea. This can be done a little bit better with Josephson junction, yes. And so the idea is put a lot of Josephson junction all together and measure these things flying by. If this could be measured, that would be fantastic, because it would confirm if we could estimate the mass and velocity of the particle flying by, so that quantum gravity predicts particle at some scale and suggests that there's this particle of some scale. Remember, a remnant stabilized by the area gap, and it will be a beautiful confirmation of the entire story with an experiment. I think this experiment is not out of reach. I'll stop here. There's plenty of things, of course, open. All the things I've told you are, sketchy and to be completed, but I think they make coherent story, and that's what I'm most excited about. Thank you.